We'll be starting shortly, just waiting for the heads up from the folks at CleveSec. To the at least one person viewing, I'm sorry for the delay. Just waiting for the folks at CleveSec to give me the go-ahead. All right. Hey, everybody. Hold on one sec. Okay. All right. Hey, everybody at CleveSec. Thanks so much for having me over digitally to talk locks with you guys. Hope you're enjoying your lock sport night. And hey to anybody else out there that's viewing this. If you want to, the best way to shoot questions to me for after the talk is to hit me up on Twitter. At shoebox, like the thing that you would put your shoes in. There's a significant delay on the broadcast, so doing the chat window or whatever else is going to be a little bit of a hassle, but I have the Twitter feed up on my tablet next to me so I can try to answer some questions as we go along. So I'm Skylar Town. I have been picking locks for 8 years, and I've been studying the history of locks and the history of security in general for the past 3 to 4 years very seriously. Recently at RVASec down in Virginia, a fantastic conference, I was given the opportunity to talk through sort of a mechanical engineering perspective on the history of security, taking us all the way back to some of the earliest known locks, right through to locks that we would see in a hardware store or a locksmith shop today. So today's talk is based on that talk, and it uses a decent amount of material from that, but I have focused it dramatically so that I can really dig into some of the core content and really establish a lot of the connections between ideas that have been going on for thousands of years. So we're going to dive right in. I'm going to share off some of my slides and switch back and forth. And I think this is my first time doing a streamed talk in years, so we'll see if this is any good. Hope you guys enjoy it. All right, so we're going to look at two different branches of the evolution of the lock. We're going to have a look at some of the basic ideas in Roman locks, and we're going to take a look at the Mesopotamian realm, by which we got some other very interesting locks. So just stepping back real quick to this first image, what you're seeing is a deadbolt. And we have this long stick, which is acting as the key. So the key for these Roman locks really was just a stick bent and passing through this hole in the door. It would be exactly long enough to dip into the small serrations that you see in the bolt there, and then shove them back and forth in order to lock or unlock the door. So it's a very simple idea. You see the primary door unit on the left, and then the third staple, the one all the way on the right, is what the bolt would actually slide into. So on the left it's locked, on the right it's unlocked. Dead simple. Okay. So we're also going to have a look at Mesopotamian locks, and Mesopotamian locks started with this Mesopotamian door seal. It's a very simple idea that just had a single bolt going through this clay seal, and the bolt would hold the door locked, and the seal would protect it from being unlocked, though really to unlock it you just had to destroy the seal. But being that it's a seal, it lets you know at least that it's been opened. So we'll see how both of these evolved and created some of the locks that we have today. So going back to that Roman idea, one of the very first things that we're going to see routinely throughout this talk is people changing up the form factor. As a matter of fact, we're going to see three things pretty commonly. We're going to see changes to the form factor. We're going to see changes to prevent the tentative method of lockpicking, which we'll explain in depth in a minute. And lastly, we'll just see people adding more pins, adding more levers, whatever the case may be. So those three ideas pop up over and over again throughout history. Changing the form factor, usually to make it smaller, changing the workings of the lock itself, or adding security features to beat the tentative method, and if a couple of tumblers is a good thing, probably adding 30 more is going to be a great thing, so we see a lot of people just adding more. So, as we go along, we'll see a lot of that. So, the very first thing we're going to look at is just the form factor being unwieldy. The Roman key, that big stick, that big bent stick, is actually mentioned in the Bible and a lot of old writing. They would talk about people walking around with their keys slung over their shoulders because they were so big. And keys were also a mark of authority and power. As a matter of fact, Athena, despite having the name of the city of Athens, was also given a key to the city to sling over her shoulder. So they're massive keys, they're super impractical, and honestly, just looking at them, you can get a good sense of how to make your own. Not that there was a lot of, amateur metalworking back then. So being that these huge keys are unwieldy, we start seeing dramatically smaller keys that still operate directly on the bolt. So with this small key, which is from the 8th century AD, and is part of the Allentown collection at the Stanford Museum, the small tab at the end of the key, that bit, will just operate directly on the bolt, slipping it back and forth, into and out of the body of the lock or the door, whatever the case may be. However, those sorts of flat keys are really easy to duplicate. So we very quickly start to see some different profiles cut into the keyway. However, whether it's a block of wood or a piece of metal, or eventually, we'll see more and more elaborate keyways as we go along. But keyways come pretty early, different shapes for the face of the key to fit into the lock. And going to the other side, if we're acting directly on the bolt, creating this really elaborate warding. So the way the warded lock works is very simple. If we look at this lock here, this key, we'll see that all of these paths that are cut through the key, the very elaborate warding, on the inside of the lock, we're actually just going to see the opposite of that. So for every zig and zag and cross and angle, we will see that reproduced in metal on the interior of the lock. So having those slight blockages prevents our access to the bolt if we don't have the correct key. And so we see more and more elaborate wardings. And in this case, we're looking specifically at a paracentric warding. And what that means is that the different lines cut through the key make it so that you can't draw a straight line from one side of the key across the other. They break the center line. They're going back and forth. We'll see this concept pop up quite a bit as well. So the problem with all of this, though, is that the entire concept is going to be doomed. Despite that, it manages to persist for thousands of years. So what we're about to look at is the birth of the lever lock. But here's the reason that the warded lock was doomed from the start. Even if you have incredibly elaborate wardings, like that beautiful paracentric key that we were just looking at, you're still going to have an easy job impressioning the key. And what I mean by this is that if you put a blank piece of metal, a blank flat piece of metal, into the lock, and you apply just a little bit of wax to that, and begin rotating your blank key in the lock, you'll stop eventually, right? Eventually the warding will catch your key and it won't let you go any further, but when you pull it out, you'll see imprinted in the wax exactly where you need to cut. So you remove that material, you put it back in, a little more wax, you turn until you get another mark in it, and as you're building up these marks and removing them from the key, you're actually creating a perfect key that will always work in that lock. And warded locks across the board were doomed to fail by that attack, and that's called the wax pad attack. So, in a direct challenge to the wax pad attack, we have the first lever lock. So this is a simple barren lever lock, and it works in a really simple way. Looking at this head on, we have a big leaf spring up toward the top. Now that leaf spring has a small peg that is pushing down into a notch in the bolt. If we look a little bit over to the right, we'll see another empty notch. And this, really, just this very simple two-notch system is the birth of most of modern security when it comes to locks. So, if we're looking at the bolt now directly, we see that there is a path that it can slide along. And behind the bolt, we'll see another small piece of metal. And that small piece of metal is going to push up on that spring, and then the key will still act on the bolt directly, and it will drag the bolt out of the casing of the lock in this case, which is to say that it will lock it, and then the key will release the bar of metal behind the bolt, and that notch will be filled by the little tab on our leaf spring. And that's it. It just drags that notch from one position to the other by sliding the bolt along. And it pushes that notch out of the way with a lever. And that lever is our first real tumbler. So the lever is really interesting because even though it potentially defeats the wax pad attack, it introduces a whole new arena of attacks, and it's actually really simple to defeat. The very first barren lever, the barren lever lock, is what we call a single-acting tumbler. So in the case of a single-acting tumbler, we literally just have to lift it high enough, just push it in one direction far enough, and we can manipulate the bolt to our heart's content. So if we get in there with a little piece of wire or a bent piece of metal, whatever the case may be, and we lift up that lever, it doesn't matter how high we're pushing it upwards. With another piece of wire, we can flip that bolt back and forth to our heart's content. Really, really easy. So it's actually not a big leap in security, but it is the birthplace of some really interesting ideas. So from the single acting lever, we then move to the closed lever. So like I said, the single acting lever isn't particularly secure, so we start seeing these closed levers where the levers have to be lifted up high enough, but if you attempt to lift them too high, they'll stop dead. They'll stop completely and won't be able to move any further. Now, this sort of makes it a double-acting situation because you can't lift too low and you can't lift too high, but it also reintroduces the problem of impressioning. Because by lifting up on that lever, as soon as your key stops, you just remove a little bit of the material from wherever it stopped. And then you try to lift it again. And assuming that it still doesn't go, you remove a little more and a little more until your key can turn completely. And now you've cut down the key to the correct depth for that lever. So we move on to the enclosed lever. And this H shape is a real leap in the security of key-based locks. So your lever, your post of the bolt that will allow it to slide back and forth, is sitting on one side of this, and then you have to lift it up exactly high enough in order for that bolt to then be able to slide between the two enclosed sections. So if you lift it too high, it won't work. If you lift it too low, it won't work. Cool, makes sense. However, we're going to see a major shift in lever locks. And we still see a lot of enclosed levers today, but in order to fit them into padlocks and smaller cases, we have the form factor problem. And thus, we start seeing levers shaped like this. So these levers are pivoting from the far right. Each of them have their own little leaf spring there that are pressing against the bar marked 64. And then over on the left, you'll see the gate marked 50 are now along the edge of the lever. They're along the face of the lever. And when the key is inserted into the lock, it will slide along that big curve in the levers that we call the belly of the lever. It will lift each of them up to different heights, and if they're lifted too low, the post, 52, can't get pulled into the lever, and if they're lifted too high, it can't get pulled into the lever, so instead they all have to be lifted to exactly the same amount, but in this new open idea, they don't have to be quite as large, and they can be fit into some very small places. So now it's time to talk about the tentative method. And the tentative method is what you know of lockpicking. It is the way to pick a lock. So by applying a little bit of pressure to the system, by beginning to slide the bolt, again with a piece of wire acting directly on the bolt, we can pull that post against the face of the levers. So we have our small post pulling against the face of the lever. We have our gate here, as represented by my, live long and prosper. So if we're not yet lifting high enough on the lever, we're just pressing the post into the face of the lever. Now, as we keep that pressure applied, we'll keep pressing and keep pressing and keep pressing, and then when we get in and apply another wire to our lever, lifting that up, we will slide up and up and up and up and up, and eventually we will feel as the post goes free and isn't grinding anymore, and it's hit our gate. So that's the entire idea behind the tentative method, and it's the same idea by which you pick pin tumbler locks and anything else. You guys are having your lock sport day. You're going to use the tentative method on probably everything that you work on. A little bit of pressure, and then manipulating the tumblers. Put pressure on the system, manipulate the tumblers. Doesn't matter if that's a lever tumbler, a disc tumbler, a pin tumbler. It all works the same way. Interestingly, tentative method linguistically appears to go back to the tentative process, which was attributed to Isaac Newton and was the birth of the scientific method. So, he describes a tentative process by which he tries an idea, allows it to fail, and then iterates on his failure. And so when we apply pressure to the system and we attempt a tumbler and we get nothing out of it, fine, but we might learn a little bit of something, and we move on and we test another and lift a little higher, change up our attack. That method of rapid failure and iteration is the tentative method. And linguistically, it goes back to sort of the birth of the scientific method, which is cool. Probably not really here or there regarding the rest of the talk, but in order to defend against this tentative method, which is incredibly powerful, powerful to the point that we first start seeing the tentative method appearing in the late 1700s, and we are still using it today to defeat almost every single key-based lock on the market. So, to begin defeating that, we start seeing some new additions to our locks. In particular, serrations. So, here we have our lever tumbler with, here it's called the sweep, I tend to call it the belly, and we have our spring above it and our gate, and then right below the gate on the right, you'll see that we have a series of small notches cut out. These are our serrations, so that when we are lifting that lever upward to try it against the post will actually catch in those little serrations. And the posts in lever locks will often be barbed as well, so that they will catch those serrations really tightly and make it very difficult to find the correct gate. And this can even go a dramatic step further. And in 1811, I believe, we are introduced to Chubb's detector lock, the Chubb brothers detector lock. Now, other people had detector locks before this, and the idea of the detector lock is pretty straightforward. When you are picking the lock, it will detect the fact that it's being picked. In the case of most of the lever-based detector locks, you would have to lift one of the levers too high, at which point the detector mechanism would snap into place and it would prevent you from manipulating any of the levers again. So in this case, we're going to look at letter C, that post extending through a gap in all of the levers is the punishing detector mechanism, so that when you lift one of the levers too high, it will push that post, which will release another sprung element, which will lock into the notch cut out of the top of the levers and prevent you from pivoting the levers anymore. Now, like I said, there had been detector locks before the Chubb, but the Chubb is particularly famous because of that key over on the right. That would reset the detector mechanism without you having to destroy the lock. Previously, if the picking attempt was taken on your detected lock, it would lock it down tight and you wouldn't be able to release it non-destructively. So the Chubb lock brought this detector mechanism sort of to the masses in a very practical way. And Chubb locks are still sold to this day. However, in the Great Lock Controversy of 1851, which of course is one of my favorite topics of research, it was proved that the tentative method can still be used very effectively against Chubb's detector locks. Because you can pick them in reverse by using the opposite key, what Alfred Hobbs did was that he used the detector mechanism to intentionally fire. Basically, he would lift a lever until it set off the detector mechanism, and then he would know that it had been picked too high. And he would make a note of that, and he would pick it in reverse in order to reset the detector mechanism, and then he would go to work on the next one. He would lift it until it went too high, and boom. And what he realized was that he could just use the detector mechanism against itself because he could pick the other one with the tentative method. He could pick it to working again with the tentative method, and then he could just decode it using the detector, which is amazing. It's a super cool attack. Okay, so from here, we're going to look at one of two beautiful French locks that we're going to look at in this talk. This is the Fichet 450, and this is the idea of just adding more. So, and it's also actually the idea of the form factors as well. So this is a very small lock on the scale of lever locks. The Ingersoll makes a really nice compact lever lock for a normal mortise door, and the Fichet 450 brings this even tighter. And the way that this works is that the key that you see in the foreground with its I-beam shape has 4 rows of cuts in it. And each of those rows operates on a different set of levers inside of the lock. And here on the face of it, we're seeing 2 of those sides. So the levers will pivot from each extreme end of the housing of the lock. And when they have arrived at the correct position, each of their gates will align with the large gap that is cut through all of them, and then the two big holes that you see on the side of the lock will contain a sidebar. And we'll look a little more at sidebars when we get to medicos in a minute, but the sidebar would just be a long bar of metal that, when all of the gaps were open, would act just like the post and slide into the aligned gates. So this had 10 levers working independently in sets of 3 and 2 across 4 axes of the key. And it's a very cool lock and significantly high security. It had its own problems, of course. It was pickable, and it could be defeated destructively as well, but they're beautiful locks that actually entered the American market for a little while. You will see them being advertised in Popular Mechanics right alongside the Norman lock, which is just an incredible, mind-blowing lock that I believe I've recently decided to eventually get tattooed on me. But recently, as in I said that to my fiance yesterday, so it might never happen, so nobody hold your breath on that. Anyway. So it's just very cool, and while you certainly can't say anything like it's the logical conclusion of the lever lock, it does bring that form factor down to a tiny space, and it adds just a silly number of levers, and additionally has false gate serrations on them. So it brings together a lot of the things that we've talked about in the first branch of our evolution of the lock into one beautiful little cylinder. And the Fichet Company in general are just one of my favorite producers of locks. All right, so let's dive in now to the Mesopotamian route. And don't forget, as we're going along, you should feel free to shoot me questions that you have over to @Shoebox on Twitter. I'm keeping an eyeball on them as they potentially come in, but I want to keep proceeding with the talk as I go too. Okay, so Mesopotamian locks. Now, Mesopotamian locks have been known as Egyptian locks for the past 200 years. I am working to correct that by calling them the Mesopotamian lock, and while I have spoken a lot about it and written about it casually, I really need to publish a paper about this research, but you can see it in various talks that I've done. Anyway, just bear with me that these began in Mesopotamia, and this, the Mesopotamian door seal, is the mechanical precursor to the lock that is on your door right now. So it should hold an important place in your hearts, if you care anything at all about locks, which I assume if you're watching this you do. So, the Mesopotamian door seal, as I was saying before, is a clay tablet secured around a piece of wood that acts as a stopper for a door sliding open. The way that it's actually strung up in the back involves some rope and whatnot, and it's a little bit more elaborate than what I'm describing. But the important thing is that that bar in the middle is called the cicatou. And that's a modern transliteration of a cuneiform word. But that cicatou, linguistically, got moved to a much more complex lock. So this is a regular go-to image for the Egyptian lock, but each of those pegs, when you look at linguistic record in the Mesopotamian security sphere, are called cicatou. So we have this linguistic evolution from the door seal to the first key-based lock, and it implies a mechanical evolution between the two as well. So this well predates the Roman lock also. The timeline that we're looking at for the creation of the first key-based lock is somewhere between 1800 BCE and 2500 BCE. So we, with the Egyptian lock, or the Mesopotamian lock, we see the first gasp of a pin tumbler system. Each of those pegs enters the bolt directly, and they're each the same length. And then your key, which will have 3 small protrusions, which match the spacing of those pegs, will actually enter the bolt directly, lift the pins out of it, and then pull the bolt out. So the keys in this case certainly have in common with the Roman lock that they act directly on the bolt, which is one of the first real evolutions that we see. And I just want to talk about that real quick, because the idea of separating the key from acting on the bolt directly provides a very rich layer of security. So as long as we're always operating on the bolt directly, we're pretty much always opening ourselves up to relatively direct manipulation. If we can access the bolt directly with a key, then we can definitely access the bolt directly with a tool meant to emulate the key. And when we can access the bolt directly, and that bolt is going to act on our tumblers, we can always apply the tentative method, right? So what we're showing you here can still, is still subject to the tentative method, but just the idea of separating the key from the bolt, the locking idea from the bolt, creates a massive new layer of security possibilities. So here we have our key in the middle of the frame, entering into these what we might now call sliders instead of normal pin tumblers, because the key is actually going through the middle of these tumblers. The bottom portion is attached to the upper portion, and we're just moving through a notch in it. So this slider idea we'll see later on with Joseph Bramah, but I think there's a really strong argument to be made for him coming up with the idea on his own, as there hadn't been much reintroduction of this idea before he started making his locks. Anyway, so now the bottom of these sliders are interacting with the bolt. The key will interact only with the sliders, and then we pull the bolt out separately of the whole system. Now, around the end of the 18th century, 1798, we have William Etten in writing his survey of the Ottoman Empire, and he's actually seeing Turkish locks that are the modern-day ancestor of the Egyptian locks, the Mesopotamian locks. And he was kind of a dick. He, in looking at the lock, said, this idea might be improved on, but the Turks never think of improving. So his survey of the Ottoman Empire began to reintroduce the idea of the pin tumbler lock to Europe. And as you can see by the very fact that we're still seeing them in 1798, this lock has persisted. As a matter of fact, you'll see it showing up in different parts of the world. Clearly, I think originally having propagated from Mesopotamia, then through Egypt, Rome, and as Rome conquered, they brought the pin tumbler lock idea with them as well. And so in the 18th century, the examples of this lock were all over the place, but it hadn't really been in the European consciousness until William Etten came back and published his survey of the Ottoman Empire. But even then, it didn't really capture anybody's imagination until the fellow on the left there, Vivant Denon, was traveling with Napoleon's army in Egypt, when Napoleon was attempting to conquer Egypt, around the same time that Etten was doing his survey. And this went poorly for Napoleon in the end, but he was also on a mission of cultural looting, basically. So he brought together his corps of savants, of which Denon was one. And Denon actually separated from the rest of the army and the rest of the corps of savants in order to chase after this guerrilla fighter, Murad Bey, heading up into northern Egypt. And the reason that he wanted to do this was because, well, there was some knowledge of southern Egypt and the areas that Napoleon was attempting to conquer. Northern Egypt was, there wasn't a lot of information there, not a lot of information available to Europeans there. So he went into northern Egypt chasing after Murad Bey. He came across this temple at Karnak. And at Karnak, he drew an illustration. No, sorry, he didn't draw the illustration. That's been the biggest pain in my hide for the past 3 years. At Karnak, he observes on a wall a carving of the lock that he's seeing all around him, the same lock that was described by Etten. So, looking at this lock, he says, man, isn't this cool that such a utilitarian object could survive these many years in the revolution of nations? What he put together in his little speech about it when he wrote up his journals was actually quite beautiful. So he brought knowledge of this and a ton of illustrations of clothing that he was seeing locally, of other carvings of walls, sadly not of the lock, and he brought these back to Europe, and they were published and then translated into English in 3 volumes, his journals of his travels with Napoleon in Egypt. So the Egyptian lock, as it was being known at the time, sparked this sort of fever of new invention. And already in England, we had this fantastic push for new security ideas, especially when it came to locks. Anyway, you can hear all about all of that in any of my 1851 talks, but let's dig back into the practical results of this period. So, one of the very first things that we see is that the massive form factor of the Egyptian locks starts to get played with by the European and eventually American inventors. And one of the big things is that the nature of sliding that bolt just takes up a lot of space. Now, Linus Yale Sr. would eventually make some sliding bolt or sliding plug locks, but Abraham Ogier, I've never known how to pronounce that, Stansbury, who has the first patent on an Egyptian-style lock, and Linus Yale Jr., of course, along with many others attempting to do some work in that space, were creating rotating ideas where the locks would actually turn so that the action of unlocking with the key would all take place in the same area, and nothing would have to be slid out of the way. So eventually, Linus Yale Jr. puts together the modern version of the lock, which we see in this famous patent. And we start seeing keys that much more clearly resemble your own. And again, this solves another problem as well. As it says at the top of the slide, fitting locks to doors suck. So when the Mesopotamians or the Egyptians or the Romans or, even to this day, folks like the Bamani of Mali and the Dogon of Mali, who to this day make hand-carved wooden locks for their houses, when they were making the locks, they had to fit them specifically to the door. So one of Linus Yale Jr.'s other big breakthroughs was taking all of this work that had been done by his father, by Stansbury, by others playing with the pin tumbler concept, and he said, okay, isn't this great that we have been able to separate the action of the key from the action of the bolt? The key is just going to unlock the basic mechanism, and then the bolt will follow along. That's amazing that we've been able to do that, and not only does that provide us another layer of security engineering, but it also allows us an incredible amount of standardization. So what Linus Yale Jr. started doing was creating one format of his cylinder. And he would create the lock. And he would make the keys that fit in the lock. And then on the back of the lock, he put something that's called a cam. Now the cam would become the universal member that would interact with every bolt. And so the cam would fit into the latch or the bolt, and it would slide it back and forth, but it would only do that when the key had been able to successfully rotate it. So Linus Yale Jr. was able to take, this long history of people cobbling together individual solutions for individual doors, and don't get me wrong, he was far from the first to apply mass production techniques to security, but the reason that the lock on your door is a pin tumbler lock is probably because he so successfully solved this format problem, this footprint problem, where all of the door manufacturers, all of the architects, all of the people making hardware could start building solutions around his one model. And then any lock that you bought from him or any of his competitors that entered the market could all fit the same doors. It's a huge moment. Anyway, so this is how you wound up with the lock on your door based on this lock from 4,000-ish years ago. So, sorry, I've just switched back to the slides. I'll get quicker at this. We also, at first, just have open keyways, where it is just flat steel. Now, if we remember way back to the start of the talk with the Roman locks that were flat, that's very easy to reproduce, very easy to get tools in there, and thus we start seeing these shaped keys, and the first patents for them refer to them as corrugated keys, and we see corrugated keys around 1880s, and it's one of the last big innovations in the core concept of the pin tumbler lock that we'll see for a very long time. So again, the tentative method will work against pin tumbler locks fine. And as a matter of fact, you watching this, especially you in person at CleveSec, should know that. Because you're all about to go pick a bunch of pin tumbler locks, most likely. So the tentative method works fine. We start to rotate the plug of the lock that presses on the tumblers in our lock. We press up on the tumblers until we feel them catch on what we now call the shear line. And when they're all caught in the right place, it'll rotate freely. Boom, tentative method works great. So, once again, just like in the lever lock history, we start to see some solutions to the tentative method problem. And just like in the lever lock history, thousands of years ago, we start to see more elaborate wardings, these paracentric wardings. Though I exaggerate a little bit. In the history of the lever locks, paracentric wardings, you start seeing more in the like 14 through 1600s. But still far predating the pin tumbler locks, you can see where they get their inspiration from. However, the tentative method still works against this, so we start modifying the pins, applying serrations to our pins. Again, in the history of the lever lock development, we definitely saw that, 100 years ago, or a little less than that. So serrations on the pins provide the same function as serrations on the lever tumblers, and they cause a lot of problems for pickers, but these locks can still be picked. Tentative method is a super strong technique. So, just like we had the Chubb detector lock, we start to see locks with trap pins. Now, what we're looking at here is actually just a way of converting a very basic pin tumbler lock into a lock that contains trap pins. It's a little difficult to explain without a lot more pictures than this, but what you're seeing on the bottom are what are called construction keying holes. Those are there in order to, it provides a single change of a key when you have built a series of houses for construction, and then the first time the user operates their key, some ball bearings or some powder will be shifted, dropped into those holes, and now the construction worker's key will never work again. So we're making use of these construction keys and some old Schlage F-Series T-pins to create a trap pin system in a normal pin tumbler lock. Which is a technique that I learned from Zeke79 on Lockpicking 101 like 6 years ago. Shout out to Zeke. You're awesome. You were one of my first and best teachers. Cool. But pin tumbler trap pins, for the most part, act just like the early detector locks, where once the plug is trapped, it will have to be destructively opened. But that can still be very important for some higher security situations. And for the person that arrives attempting to non-destructively open a lock, having to suddenly switch to destructive entry might foil them completely if they haven't come prepared to do both deeds. So it's definitely a strong new mechanism, but they can definitely still be potentially defeated if you're really clever about how you're doing your work. All right, so still attempting to defeat the tentative method, we start to see something called Lafayette locks. And many of you may have seen a very modern Lafayette lock recently with the Forever lock pictured over on the right. But we see patents for these very early on. And the one on the left here, made by Linus Yale, is not even the earliest. And I very excitedly have right here in front of me the earliest Lafayette-style lock ever made. So this is a herring lock. The patent for it was 1848, and it was later reissued in, I believe, 52, but this is from the 48 patent, and amazingly, it is a cutaway so that you can actually see the tumblers. And when we look on the inside of it, it's also painted. And I covered this in one of the videos on my YouTube channel. But this is a salesman's sample of the first ever Lafayette-style lock. So this is how it works. This is the key for the lock, these little pegs. And we're going to slide this in this little slot up above the handle. And as we press this in, you can see, oops, sorry, let me get that settled. Oh, so finicky. There we go. As we press that in, you can see the levers sliding into position, and then we're actually going to start to close the handle. So we close that slot, and we no longer have access to the key whatsoever. So the whole idea behind this locking concept is that you put the key in the lock, and then the interior components of the lock hold the key in place or put the key into the right position and then attempt to draw the bolt. So you can't get in there and tension something and then manipulate it like you would with the normal tentative method. It completely cuts off your access to the levers before the bolt is able to act on the levers. So now the bolt is able to come in, and when we come all the way back around, it'll spit our key right back out for us. This was clearly being sold by somebody that didn't 100% know what they had on their hands, so I got it very affordably considering what it was, and it is my favorite lock in my collection at this point. So, Lafayette locks are super cool, and they're cool to the point that they keep coming up. And when I started seeing covered in Gizmodo and Boing Boing and all the hell over Twitter and everywhere else, the Forever lock, this I believe Taiwanese or Japanese bike lock that, let's show you the picture of it again. So the idea here is very similar. This, all of the red bits there, the part that slid out to the right, opens up a channel for you to stick your key in. The key is the little silvery bit with sort of the notch taken out of it there. And that slides in like you would, you know, shuck a torpedo into a hole. And then you rotate, close the red part into the other red part, and then rotate again, and that key is brought into the right position to open up the bolt. Sorry, not the bolt, but the U-shackle. Okay, so this is all well and good, except that Ollie Dietrichson, Ollie, please forgive me because I'm sure I'm getting your name completely wrong. But Ollie, one of the amazing pickers that I've had the opportunity to meet out in Holland and Germany, actually put a YouTube video up of him bumping this. He made a bump key out of one of the keys for the system, and then he notched it in place and then whacked on the actual end of the lock, and it held it in place for him perfectly and allowed him to bump it open. So even these Lafayette-style locks, which completely take the key and the tumblers away from you, can still potentially be manipulated. It was a super, super clever attack. Okay, so Lafayette-style locks remain very, very cool, though, and it was neat seeing some new ones pop up, and it gave me an excuse to yap at a bunch of people about history, which is always my favorite. So in addition to all of this, we have secondary locking mechanisms. So if you're attempting to create a higher security system, you always want to build in additional layers. So this idea of secondary locking mechanisms initially just takes the form, just like it did in the lever locks, of adding more tumblers, right? So we add more pins in here. So this is a DOM in the IX series, probably in IX10, I think. I actually have a belt buckle of the DOM IX10 key. And this just provides 2 rows of pins, which creates a bigger problem. And there are a lot of other beautiful things about this idea of the lock, but let's keep on moving along. So we also have what are called cruciform locks. So instead of 2 rows of pins, we have 3 or 4 rows of pins in across. Now, interestingly, before the inline pin tumbler lock was invented, Linus Yale Sr. was initially playing around with cruciform locks. Now, in his locks, he would only wind up having 4 pins, but a lot of modern cruciform locks can have, 16 pins without too much hassle. And then, if you want to have the most pins, just look to anything that Kaba is doing, K-A-B-A. This is the Kaba Star, which has, I think 6 racks of possible pin placements, 20-something potential pins, because not every single chamber can be filled in every single configuration. But regardless, the number of possible pins to put in this thing and the number of key differs is just astronomical. Absolutely absurd. So adding all of these pins is all well and good, but we can definitely still pick them. In fact, the more pins you add to the system, particularly in the case of things that not only are adding a large number of pins, but also still want to fit into the same footprint. If you think about a normal pin tumbler lock, a normal pin tumbler key, the cuts in the key correspond to the length of the pins, right? So if you have a really deep cut followed by a really shallow cut, that's a really long pin followed by a really shallow pin. Cool. in a cruciform lock that is made to fit into the same footprint as a normal pin tumbler lock, the amount of variation from one pin to another pin is very, very small because there just isn't enough room to have the larger variations that we get on normal inline pin tumbler locks. And therefore, they can actually be raked a lot easier than normal inline pin tumbler locks. So the tentative method will keep blasting through just about anything you throw at it. But there are some more novel ideas in here as well. So we're looking now at Medico. And Medico had this idea of having their pins rotate. And the way that this works is that the pins, which you can see illustrated in the lower right-hand corner here, have a chiseled tip. And then the key, which we see dead in the middle over on the right, the cuts of the key, instead of being straight across, are cut to different angles. And the different angles the pins are cut to correspond to a gap cut out of the side of the pin. Now, we've seen gaps like this before when we're looking at the sidebar on the Fichet 450, when we're looking at just the way that lever locks work in general. And here, Medico is now introducing the concept of a sidebar to pin tumbler locks by cutting a gash out of the side of them, cutting gates into the side of them, so that when the pins are lifted and rotated by the key, each of those gates are facing the same direction, and a bar of metal, a sidebar, just like in the Fichet 450, which in this case we see basically right in front of us down toward the bottom of the lock. There's a bar of metal running all the way across the cutaway. That's our sidebar. So when the key is fully inserted, all of the pins are lifted to the correct height so that the plug can rotate with the normal, pardon me, so the plug can still rotate as normal with the shear line clear. And the sidebar also has to drop in order for the plug to rotate and the sidebar to pull out of the housing plug, the lock. However, the tentative method does something really interesting here. So the whole idea behind the tentative method is that we're applying pressure to the system and then manipulating the elements of the system, tumblers. So in systems that actually add secondary locking mechanisms that are divorced in some way from the primary locking mechanism, in this case we have rotation divorced from height. So the pins have to be lifted to the correct height to solve that locking problem. It doesn't matter if they're rotated in the right direction to solve that. Similarly, they have to be rotated in the correct direction to solve the sidebar, but it doesn't matter what the height is. There are exceptions to this, but in the classic Medico, this is the case. So when you apply pressure to that system, the whole reason the tentative method works is that nothing is actually perfect. And so when you're applying pressure to one thing, another thing isn't quite yet binding. But you just deal with the one that's binding, and when that one moves, now you're hitting another one. And then you find that one, and when that one moves, you go in a little bit, and you're hitting another one, and so on and so forth. Well, the same idea applies on a larger level if you think about separating this rotation from the lifting. So I learned this from John King, J.K. the CJer, who created the Medicoder. And I got to do some work with him on the disclosure of that and publishing some stuff about that. And he was the one that really introduced me to this idea that you can just detect one of these mechanisms at a time, and the slop between the two mechanisms means that you can manipulate just the heights, and then when that's all in order, the lock will turn a certain amount, and now it will engage the sidebar. And now you can work on the rotations until the sidebar locks in. Or, if you're rotating in the opposite direction, do all of your rotations, lock the sidebar in, and it will hold them in place while you now deal with the height manipulation. So this is still very hard. This is not an easy thing to carry out, but it gives us a method of attacking it. The tentative method provides us a means of circumventing even these higher security ideas. So we then have this amazing little lock, the M-Heart interlocking cylinder. And I do a video on this in my recent collection series as well. But the basic idea, if we look all the way over to the rightmost pin stack in the right picture, what we see is that the key pin, the pin on top, and the driver pin, the pin on the bottom, are actually interlocking with one another. They're linked together. And as a result of being linked together, you have to both lift them to the correct height and rotate them at once. You can't separate those ideas anymore. They have to be both lifted and rotated in order for the plug to turn even a slight bit. And so the tentative method still applies here. We can still attack this lock. We can still pick this lock. I personally have never picked one, but I know people who have. But it makes it dramatically, dramatically harder, and is just a great evolution of the previous. Okay, so then Linus Yale Jr. comes along, and in the aftermath of the Great Lock Controversy of 1851 and a lot of other stuff that he sees going on, he comes out and says something painfully flowery, but the gist of it is any lock that can be opened by a key can be picked. Basically, if you can get a key in there, we can carry out the tentative method on this. We can find a way to manipulate it and open it. So he starts turning his attention, and a lot of other people have the same idea and start turning their attention to combination locks, what are being called at the time permutation locks. And there are a lot of these out there. We're going to very quickly knock off the sesame lock, what you're seeing on the left, and I don't have a great name for this, but ever since that Dan Brown book came out, I've been calling it the cryptex lock, because he calls it the cryptex in that book. Seems like a decent name for it, where the tumblers spin around the interior locking mechanism. So the problem with both of these is they can be really easily brute forced, and they can be really easily decoded. So remember our sidebar? Well, we're going to reintroduce the sidebar, but now we're going to call it the fence, and we're going to build in a bunch of gates to our system. So because we can manipulate each of the individual tumblers in our other permutation locks, because we can manipulate those directly, put our fingers on them and twist and go, brute forcing them is a very fast affair. Really, really easy. Even if you have, 4 wheels, even if you have 5 wheels, comparatively to brute forcing your way through any other lock that you have to deal with different tools and whatnot, because you can just use your fingers, super easy, super fast. So what we're looking at in this slide is these 2 little bits of silver metal that you can see right in the middle that are sandwiched between the brass discs. Those are called flies. The whole idea behind a fly is that you are only manipulating the backmost wheel in your combination lock. So you're manipulating the back wheel, and then it has a small peg of metal, and that small peg of metal interacts with a small peg of metal in the next disc, and it, as you rotate it, picks up the next disc and begins rotating that one. And that has a little peg, and that manipulates the next one, and so on and so forth. And this is the reason that when you're dialing in your locker combination, you have to rotate however many times in one direction, and then one fewer time in the other direction. Because you're picking up from the back wheel, and then you're rotating until the front wheel is in its correct position. And then you start rotating the back wheel in the opposite direction, pick up the next wheel, leave that one where it needs to be, and then do it one fewer times, and then with the wheel that you're directly manipulating, you don't pass go again for that one. So that's how those work. But we come up with some interesting methods. Oops, sorry. We come up with some interesting methods to attack these as well. So the problem here is that it's really easy to feel where the fence interacts with the gates in the wheels. So we're just trying to line all of the gates up in the wheels, and the fence can drop into it. But if the fence is acting on that directly, it's really, really easy to feel where each of those gates are, and we can very quickly determine what the combination should be. So we add the nose, which is the big protrusion off of the fence, pushing down into the gap of the what we call the cam wheel. That's the one that you're manipulating directly. So that's all well and good, but then they come up with the micrometer attack. The micrometer attack is really cool. What they're doing is testing the distance between feeling a tap on the right side of that nose and the left side of that nose, and just testing that over and over again as you rotate all of the wheels in turn. It's a really cool attack. You can read a great paper about it by Matt Blaze at crypto.org called Safe Cracking for the Computer Scientist. It goes into this in depth. And so there are ways to combat this, though, because what this is doing is trying to align all of the tumblers, and then feel the back of it. So one of the ways to defeat this is to create oblong wheels so that the fence is lifted up a little bit higher and a little bit lower depending on which of those slightly ovoid wheels is manipulating the fence at a given time, and that makes it really hard to feel what's going on there, and it dramatically extends the time that the micrometer attack takes. I wish I could remember the name of the first people that did this, but also just putting a ball bearing detent in the back of the lock so that every position you turn makes a loud clicking noise and you feel the vibration of it as well, makes it very difficult to measure the distance between the gate on the cam wheel and the nose. And then Sargent came along with the magnetic fence, and this thing is super cool. The basic idea is that the big red painted job on the top has a significant magnet behind it, and the fence with nose attached will actually be stuck to the magnet most of the time, but every 360 degrees, once every 360 degrees, the connection between the magnet and the fence will be broken, so the fence can potentially drop into place if it has been put into the right position, and if it hasn't, it gets lifted right back up to the magnet and held in place, so you can't feel anything except for that one moment in each rotation when it drops. And Sargent claimed, and I haven't seen anybody who's combated this claim, that with this invention, he managed to completely defeat the micrometer attack. However, you won't really see it around anymore because there are all sorts of other problems that magnets cause and all sorts of other ways to potentially defeat or change magnets. That said, really cool idea to attack a really specific problem and incredibly successful at what it did. All right, so I'm definitely running low on the amount of time that I had planned for this. I'm going to go quickly through this next little batch about abloy locks and distantainers in general. But what if we wanted to make this really small and add a key back into the system that we said we were making so that we wouldn't have a key? Well, then you would have the abloy, invented in the very early 1900s, maybe 19-aughts, maybe 19-teens by a gentleman out in Finland whose name I'm not going to try to pronounce right now, but became known as the Abloy Company, and then distantainer locks proliferated from there. That said, the amazing gray man who published an encyclopedic high-security locks, an encyclopedic guide to high-security locks, something like that. It's an amazing book. He potentially posits in that maybe the Germans saw the distantainer lock first, and then Finland got it after that. However, the tentative method works just fine against these as well, because the way that these work is that the bar of metal, the sidebar that we see on the top, is drawn into the gaps in the discs by applying a little bit of pressure to the plug of the lock. And you can apply that pressure with a small tool, manipulating what is called the zero disc, which hits the sidebar and starts drawing it into place, so it hits that zero disc, and then you can manipulate each of the individual discs with the tentative method. However, abloy, in its most logical conclusion, this is a picture of the Abloy ProTech. The Abloy ProTech has, since I last gave this talk, been provably picked with tools, and so while I said they solved it here, it has instead been solved again in the ProTech 2. The whole idea behind this is that the basis of the tentative method is that when you apply pressure to the system, you then manipulate the tumblers. So what Abloy set out to do with the ProTech, and now the ProTech 2, is that they created a system with their return bars so that when you apply pressure to the system, you can no longer manipulate the tumblers. You're free to manipulate the tumblers and then apply tension to them, but at that point you're just brute forcing, and making tools to brute force that sort of lock is just, you're playing blind. So by separating tension and from manipulation, that's the holy grail of defeating the tentative method, and they achieved it so far with the ProTech 2. We'll see what its future looks like. But the ProTech 1 stuck around for a long time before being provably defeated. All right, let's dig into the last section here, and then I will attempt to answer a couple of questions, and then I will go have dinner. Okay, so even with a system where you can manipulate, where you can separate tension from manipulation, the keys are still basic mechanical keys, and it is incredibly easy to duplicate them. Even if it's a crazy-looking key, it becomes really easy. You can get a blank for it and mill into it. You could potentially make an impression of it with a piece of clay, whatever the case may be. But it's easy to duplicate keys. So one of the first ways people attempt to protect themselves against this is by filing patents for the keys. So the Schleich Primus is patented, sure, but Only 4 of those patents on the Schlage Primus are utility patents. 2 of them are design patents, which protect their keys from being reproduced by anyone else but Schlage, so that when they're disseminating blanks for their locks, nobody else is allowed to disseminate those blanks. However, the ILCO Corporation went up against the Best Corporation in California Supreme Court, and the California Supreme Court basically said, ha! You can't do that. ILCO are welcome to knock off as many of your keys as you want. We don't think you should have a patent on that. And so far, it hasn't really been tested in a significant way again. So people definitely still take out patents on their keys, but whether or not those patents are valid in American courts is really up for grabs. So, seeing on the horizon this patenting problem, a lot of European companies started actually taking out trademarks on their locks. They would actually take the pattern cut into the plug, the pattern of the keyway, and they would trademark that. So we have your DU trademark on the one on the upper left, the SP on the lower left, and so on and so forth, so that the shape of that was a mark of the company, representing the company, and therefore it was protected by trademark. So if somebody attempted to reproduce a blank key for that, they would actually be infringing on their trademark, just like if you made a key that said Coca-Cola and tried to sell it to everybody. It's an interesting attempt, and we are yet to see a serious legal challenge. I shouldn't say that. I'm not 100% up on current legal filings in this domain, but I at least am yet to see a serious legal challenge, but it is, a lot of people think, dubious at best whether or not this would hold up. So then, really putting the nail in the coffin of patenting keys, the French Patent Office came out and explicitly said, nope, we will no longer be issuing patents to people that just have bare metal keys. You have to have some sort of interactive element, some moving element in the key itself. So here we have the multi-lock interactive, and other people had already been playing around with the idea of movable elements. What goes on here is that this floating element in the key has to go into the lock flat and then be lifted up once inside of the lock to push an element above the plane of the key. And thus it becomes incredibly difficult to reproduce a key like this, and many of you may have recently seen some of the incredibly hyperbolic articles talking about 3D printing keys and how it's just destroying security, blah, 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 and your lock is no longer safe. That's all well and good, except that for the past several decades we have had, well, the past couple of decades at least, we've had keys that can't be reproduced with a 3D printer, that can't be reproduced with a simple, mold or impression. These movable elements create a much bigger challenge, and they're yet to be solved by something as simple as a 3D printer. Don't get me wrong, people are coming up with really creative solutions for potentially recreating these, but it is an incredibly high hurdle to climb if you're just trying to reproduce the key. All right, big finish. This I don't yet own, but would probably really challenge my my herring in the hall. Well, sorry, I said there was a herring lock before. It's actually William Hall from Brookline, Massachusetts, that invented that first of the Lafayette style locks. Anyway, this here is the fichet, and the fichet is amazing. Every component inside of the fichet is exactly the same as each other. So you see 31, 31, 31, 31, 31. You see 44, 44, 44, 44, 44, so on and so forth. All of the tumblers in this are exactly the same as one another. All of the sidebar elements are exactly the same as one another. The way that this works and the way that the key has been patent protected is that Fichet said, okay, that's all well and good that the French Patent Office wants us to have a movable element to get a patent, but we're a French high-security lock company, and we are cleverer than that. So what they did is they actually patented the key as part of the assembly process, because this lock is coded the first time when a key is inserted into it, and all of those identical tumblers are turned to slightly different positions based on the shape of the key. And then the sidebars are attached to the tumblers, and the position that the sidebars are attached to the tumblers becomes the position that you receive the lock in, and it is now coded to your key only, and the lock was able to be patented as part of that assembly process. Now, all of that said, Fichet did actually go through and create the Fichet 3D with a movable element in it as well, but it was a really clever end run around that entire process. So this has been the talk. I'm going to put up the thank you slide in a minute and let that one see me off to dinner, but I did get, let's see if I have any questions. Interesting how software security mimics many concepts developed for locks. Intrusion detection, defense in depth, etc. Yeah, no, that is my bread and butter. It is the reason that people at various hacker conferences and corporate conferences ask me to come talk about locks, because there are incredible parallels in the development of physical security that apply directly to digital security. And those times when the two overlap with each other, like digital door locks that have to have mechanical elements inside of them, it tends to be a disaster, and it's really good to know your mechanical security history as well. That was Marius Ledding. Thank you for throwing that out. Jeff Popio asks, where did I get that lock? This I actually got at auction. Got it at an auction house along with a couple of others. I was watching remotely. I think it was somewhere out in Virginia, maybe. Honestly, some of the other locks that I got were crazy, and I got them for about $5 a piece. This one cost significantly more than $5, but I think only because it was so massive and people that were attending in person thought that it looked pretty cool for architectural salvage. I didn't know at the time that it was a salesman sample, and when I got it, I swear to God when this arrived and I opened it, tears literally came into my eyes. When I first saw it listed, knowing the Hall lock and having seen one recently at the largest safe auction ever in Denver, Pennsylvania a couple of years ago, the photos of which are on my Flickr page, I saw one on a door, and I really did. I choked up when I saw that I could potentially own one, and when it was actually in my hands and I understood that it was a salesman sample, tears literally came to my eyes. That's how crazy I am about this stuff. And other people are just saying thank you. At least one person is saying, could I please make a stream that works in Germany? I'm so sorry. I know that you're not seeing me apologize for this, but I will apologize on Twitter. That's lame that it doesn't work out there. And looks like that is it for now. Awesome. Thank you all so much. Oh, somebody's asking if I played around with 3D printing keys much, and do I think it is the future of locksmithing? Great question. Super on point to the end of the talk. Yeah, as a matter of fact, what you should do is check out the work that I did with Nirav Patel. That's Nirav Patel. And if you Google Nirav Patel and Schuyler Town, all in the same query, you should find the work that we did on 3D printing ABIS Plus 8850 locks, ABIS Plus profile disk detainer keys. And honestly, it actually opened up a whole new realm of exploration of semi-solid material self-impressioning attacks against disk detainer locks, which I think are the future of attacking disk detainer locks, certainly. And do I think 3D printing is the future of locksmithing? Potentially. We're getting to the point of commoditization, and we see things like, it's not 3D printing yet, but we have services like KeyMe and Keys Printed. Damn it, I feel so bad. The people that used to be Schlussel, who are awesome, and I've bumped into once or twice in comments in other internet forums, that can take a picture of your key and send you a copy of it. The same idea will apply with 3D printing and is already starting to be applied to 3D printing. I love the idea of looking at it as a possible, commoditized solution to some problems, more so than a super impressive attack vector, because the solutions to that as an attack vector already exist. Hopefully it means that we'll start seeing more and more of those solutions rolled out into the real world and hit a more consumer price point. And certainly, it would be great if we just had a threshold of knowledge among consumers of these sorts of products to begin with. And maybe in that regard only, the hyperbolic reporting is doing some good. All right, looks like that's it for me for now. Thank you all so much at CleveSec. I really appreciate it. I'm at Shoebox on Twitter. Hope that this was informative. And of course, this will be up for any of you joining late to view later on. Awesome. Thanks, guys. I'm off to eat a burrito.